Hello everyone. Today we'll see about optimizing algorithm for finding longest common subsequence in design and analysis of algorithm. First, the longest common subsequence problem is a fundamental topic in the field of design and analysis of algorithms. This presentation will explore various techniques used for optimizing algorithms to efficiently find the longest common subsequence in different contexts. Definition of longest common subsequence. What is longest common subsequence? A longest common subsequence of two sequences is the longest sequence that is appears in the same order in both sequences, not necessarily contiguous. It is a crucial problem in string processing and has applications in various domains including bioinformatics and data compressions. If we use brute force approach, the brute force approach involves generating all possible sequences of the given sequence and finding the longest common subsequence. While conceptually simple, this approach has exponential time complexity, making it impractical for larger sequences. If we use it with dynamic programming, it offers an efficient solution to the longest common subsequence problem by storing the results of overlapping subproblems. This approach significantly reduces the time complexity to a more manageable level, make it a popular choice for optimization. Optimizing dynamic program. In several techniques used, such as memorization and tabulation, can be applied to further optimize the dynamic programming approach. For finding longest common subsequence, these techniques aim to reduce redundant computations and improve overall efficiency. In this video, we are going to see an example that is with tabulation. If we see space optimization, in addition to time complexity, optimizing algorithms for finding longest common subsequence also involves minimizing space usage. Techniques like rolling arrays and space efficient matrices are employed to achieve space efficiency without compromising performance. As I told before, we have an example with tabulation technique. Longest common subsequence with using bottom-ups, that is tabulation. We have two strings. For string 1, A, G, G, T, A, B. String 2, G, X, T, X, A, Y, B. We have 6 alphabets in first string, 7 alphabets in second string. As we see the tabulation, there is one more extra column and one more extra row. That is, we need to first fill it with zeros. Every time the first row and first column will be zeros. In second step, we have a small base case, that is, if the alphabet from string 1 matches with the alphabet string 2, then we need to add +1 with diagonal number, or we need to take the maximum number of adjacent or like the column or rows from sides. From here we can see first A comma G is not matched. So we took from column 0. A to X is not matched. So 0. A to T not matched. So 0. A to A matched. So we took +1 from diagonal side. And from A to Y we took it is not matched, but why it became 1? That is the question. As we told before, the base case is if it doesn't matches, it will take the maximum number from rows or column. We see that 1 is the maximum number than 0. So we took 1 and A, B is not matched, but we took maximum number from row. We completed first row. Now the third step will be finding the second row. As we see, first value matched with G and G. So we add +1 with diagonally. And Gx is not matched, we took maximum number from row. Gt is not matched, but we took maximum number from row, that is 1. And Ga is matched. There is both column and rows maximum numbers are same. So we can take from anywhere, but we prefer column. So we took from column. And GY is not matched, but we prefer maximum number from the side of column. And GB also not matched, but we took maximum number through column. The fourth step will be finding the third row values. So again this same. From GG it matched. So we took diagonally plus 1. So it will be 1. From GX it not matched. We prefer if the both row and column has same number, we'll prefer having columns as the first preference. We can see the third row, everyone we took from the column, not from the row. And Gx is not matched, Gt is not matched, Gx is not matched, Ga is not matched, Gy is not matched, Gb is not matched. Now the fifth step is to find fourth element. We can see Tg is not matched, but we took maximum number from column. Tx is not matched, we took from column as maximum number. Tt is matched, so we add plus 1 to the diagonal number. So the diagonal number is 1 plus 1 equals to 2, so the value will be 2. Then Tx is not matched, but we took maximum number from row. We prefer column when we have both row and column numbers are same, but here 2 is greater than 1, so we'll take 2 through the road side. Ta is not matched, but the maximum number is 2. Ty is not matched, but the maximum number is 2 by the side. Tb is not matched, and the maximum number is 2 in the row. Next, the sixth step will be finding fifth element. In the fifth element, Ag is not matched, but we took 1 because it is the maximum number in column and row. Ax is not matched. We took maximum number as 1. At is not matched. So we took maximum number as 2. From the column, Ax is not matched. So it will be taken from the column, and as I told, both row and column has same number, so we prefer column. A is matched, but so we need to add plus 1 to the diagonal number. The diagonal number is 2, so we'll add 2 plus 1, 3. Ay is not matched, but we take maximum number from the row. AB is not matched, we took the maximum number from 3 to 3 is maximum. The last and final step is to find sixth alphabet values. Here BG is not matched. So we have 0 and 1 as row and column values. 1 is the maximum. We took the value as 1. BX is not matched. So we took value 1 from column. BT is not matched. We took value from column. The maximum number is 2. Bx is not matched. The maximum number is 2. Even the row has the same number, but we prefer column as first priority. BA is not matched. 3 is the maximum number. BY is not matched. 3 is the maximum number. We take the priority from the column. B matched. As we know, if it matches, we need to add plus 1 with diagonal number. So 3 plus 1 is 4. We completed the table. That, that is the how we find longest common subsequence with using tabulation. It means bottom up. In conclusion, optimizing algorithm for finding longest common subsequence is a critical area in the field of design and analysis of algorithms. By employing techniques such as dynamic programming, space optimization, and parallelization, efficient solutions can be achieved with significant real-world impact. As long as we can remember those base cases, we can find easily. Thank you.